Okay, good morning, everybody. So welcome back. So for today, we have to cover a lot of ground on chapter number 7, and I will make this recording available for you, and then you can watch at your earliest convenience. Just make sure you watch before the class on Thursday. So for this week, we will have in-class assignment on Thursday. Okay. Okay. So let's pick up where we left for the last time. So last week, the last thing we talked about was the consequences of the Bohr atomic model. So we realized that the electrons are moving in orbits around the nucleus. So that was not such a new thing because we kind of knew that before. A very important quantization of energy and radii. So remember that quantization means that the energy or the radius can only assume determined values and nothing in between those. We also used the orbit model to build a relationship between orbit changes and emission to explain the observed emission spectra of hydrogen. And Bohr realized that maybe the classical mechanics might not be ideal to describe the atom. So the Bohr atomic model was an important step, but it was a very bad atomic model. And the first problem in this model is that predicted exactly the position of the electron, and that goes against the Heisenberg's uncertainty principle, which states that it is not possible to determine simultaneously the position and moment of a particle. Because the linear moment is correlated with speed, we can rephrase the uncertainty principle as it is not possible to determine simultaneously the position and speed of a particle. So imagine the following situation. We are all locked in a dark room and we are moving in random motion inside the room. And one of you wants to determine the position of someone. Just the fact that you determine the position of someone, you have to touch someone, therefore you are changing the trajectory of the movement of this person. That's why you cannot determine at the same time with precision, position, and speed of a particle. So let me switch screens and let's see if we can draw something here. So the idea here is that imagine that we have an object moving in a straight line, and we want to touch this object to determine exactly the position. Just the fact that we touched the object, we will change the direction of the movement, and that's why we cannot determine with precision position and speed at the same time. Okay, so that's what the Heisenberg's uncertainty principle states. Therefore, the Bohr atomic model violated this principle because it was telling us the exact position of the electron, and that's physically impossible. The second problem is that the light, or actually any body in movement, has a duality wave particle. So there was a big discussion at the end of the the 18th century. What was the nature of the light? Some people advocated for a wave nature of the light because light behaves as a wave when there is diffraction and the formation of shadows. So therefore, light is a wave. However, Einstein studied the photoelectric effect, and the only explanation possible that would explain the data obtained was that light had to behave as a particle. So therefore, the other part of the community advocated for the particle nature of the light. So at the end, Louis de Broglie came to the conclusion that light will behave as either a wave or a particle depending on the situation. Okay, so light can be wave or can be particle. That depends on the situation that the light faces. If we combine the energy of a body given by the Einstein equation, mv squared, and the Planck's equation for the energy of a wave, E equals to Planck's constant times the speed of light divided by wavelength, we get to the de Broglie equation. Okay, so the de Broglie equation will describe the duality of the wave particle duality of any body that moves. Okay. So the equation says if we have a particle that has mass, unit here in kilograms, and this particle is moving with a speed v, unit meters per second, this particle will also behave as a wave, which will have wavelength lambda, in meters, and here we have a correlation with the Planck's constant. Okay, and the Planck's constant is 6.63 times 10 to the minus 34 joules times seconds. Okay, so this equation correlates the duality wave particle. Any particle with a mass and a speed will have also a wave behavior. And the wavelength associated with the movement of this particle is given by the de Broglie equation. Okay, so what we have right now is that we cannot determine the exact position of an electron, for example, and also the electron or any kind of particle moving at higher speeds will behave as a wave and also as a particle. Therefore, we need an atomic model that takes all of this into account. And that's where I want to start introducing the next atomic model, which is the Schrödinger atomic model. Okay. switch back to PowerPoint. Okay, for the Schrödinger atomic model, now we are going to use the idea of probability to find an electron in the space instead of trying to find its exact position. And that's the genius call from Schrödinger. We are not trying to find where the electron is, but where is most probable to find it. Also, we are going to introduce wave functions to account for the duality wave-particle. So we will not treat the electron as a classical mechanic body. Okay, so we now are going to treat it as a particle and also as a wave. So introduction of wave functions. And in this model, we will work with regions where the probability of finding the electron is high. That's the idea here. We are now going to use probability instead at defined position. And here is the famous Schrodinger's equation. So anyone can write this. If we have a wave function called psi, and we apply an operator to this wave function, here is the Hamiltonian operator, we will have in return the psi function plus times the energy. Okay, so h psi equals to e psi. So we will not dive into the solutions of the Schrodinger's equation. That will be subject for upper classes. Okay, so now we are going to use the idea of probability. So under normal conditions, imagine that someone will track everything you do at each hour of your day. So starting at midnight, so in the morning, probably you are going to be found in your house. So this person is going to take notes of every hour of your day and where you are. So in the morning, it's most likely that you are going to be in your house. At 8 a.m., you go to the classroom and stay there till around 12 or 1. Then you go for lunch and you have a 2-hour lunch break. After that, you go back to the classroom for more classes. After the classes, go a little bit to the library to study a little more. And then it's time to go back to the house and sleep. So each dot would be each hour of your day. And imagine that this person follows you throughout a month. The report that this person will show us is that you spend a lot of time in your house, followed by classroom time, then kind of the same time dining and in the library. So with that, we can map the probability to find you as a function of the time, for example. So if we draw a graph of the probability to find you as a function of the time using these dots, what can we draw? So let's move back to the iPad. Okay, so I will draw a graph where probability is the y-axis And doesn't matter here the label of the x-axis, but let's say is the place to find you. There are a lot of dots for your house. So we are going to say that it's high, the highest probability is to find you in your house. The second place that's most probable to find you is in the classroom. So the probability will decrease a little bit, but it's still high to find you in the classroom. Then it decreases dramatically, and there is a small probability to find you dining, and kind of the same probability to find you in the library. And after that, there is theoretically no probability to find you. So that's the idea that we are going to use for the Schrodinger model. Where are the regions where the probability is higher to find an electron? And where are the regions where the probability is lower to find an electron? So again, we are not working with fixed positions. We are working with probability across the space. Okay, and then, therefore, the goal of this model is to use equations in order to describe the probability behavior of the electron. So imagine here that we have a positive nucleus and an electron is moving in all the directions. So let's call here Z, Y, and X. So if we can take a picture of what the electron does, is that sometimes it's here and starts to move in some sort of random motions. And if we can take a picture of every step that the electron does, so we will end up with something like that. In this region, we are going to use mathematical equations to describe the probability as a function of the time, for example. Because we are working in 3 dimensions, in a 3D space, we can use the Cartesian coordinates x, y, and z. However, it's more convenient to use polar coordinates. What are the polar coordinates? So imagine that we have this position here. The distance between the electron and the nucleus is labeled as r. So we are going to have r. Then the angle between the vector r and the z-axis, that's going to be labeled as theta. So r theta. And then finally, we have the projection of the r vector in the xy plane. Right here, the projection. And the angle between the x-axis and the projection, that's labeled as phi. So therefore, polar coordinates, they define the position of the electron in the 3D space using r, which is the distance between nucleus and electron, theta, which is the angle between the vector r and the z-axis, and phi, which is the angle between the x-axis and the projection of the r vector in the xy plane. Okay, so polar coordinates are much easier to manipulate than Cartesian coordinates x, y, and z. And that's the reason that we are going to use polar coordinates. So every time that you hear r theta, and phi, this image here has to come to your mind. And with that, we can use wave function equations, and we are going to use as a function f as of r, theta, and phi to describe the behavior of the electron. To simplify the problem, there is a first part of the equation represented by r and l as a function of r, and that's called radial wave function. The radial wave function is related with the distance between electron and nucleus, okay? So it's highly correlated with the polar coordinated r. The second part of the wave function equation that describes the probability of the electron in the 3D space is the function YL ML as a function of theta and phi. And that's called angular wave function. The angular wave function is related with the spatial distribution of the electrons, okay? So it's going to be more related with the angles, not with the distance, okay? So more related with shape instead distance. I didn't forget anything. Okay, so now it's a good time to split this whole wave function. So let's talk about the radial wave function, and then we will move on to the angular wave function. So remember that the combination of these two will describe the probability to find the electron in the space. Okay, so let's start with the radial function, which is the first part of the equation. Uh, the wave functions that describe the R and L are dependent on two quantum numbers. So now I would like to introduce this term, quantum number. The set of all the quantum numbers will describe a unique electron. For the radial wave function, the two quantum numbers that have a lot of weight in it are n, which is called principal quantum number, and L, which is called angular momentum quantum number. And that's the beauty of the Schrodinger model. Mathematically, there are only a set of possible numbers for n and L that will solve the wave function. So those quantum numbers are not random numbers. They have a mathematical reason for the values. Let's start with the principal quantum number, n. The principal quantum number is basically the shell number and must assume only integer numbers starting from 1. Okay, can be 1. The next possible value is 2, 3, 4, and etc. The angular momentum quantum number, L, is related to the electron's spatial distribution and is a function of n. Okay. For a given n, only some values of L are possible. L must assume only integer numbers starting from 0 and going all the way to minus 1. The reason that L must assume only those values is that if it is a different value from that, there is no way to solve the Schrodinger equation. And that's a violation. We have to be able to solve it. Okay, let's see here two examples. In those examples, I want you to understand the correlation between L and N. Remember that N is the principal quantum number, which is basically the shell number, and L is the angular momentum quantum number, and it's related to the electron's spatial distribution. Okay, if N equals to 3, what are the possible values for L? Well, let's see the definition here. L first has to be an integer, must start from 0. So the first possible value for L is 0 and can go all the way to N minus 1. For this case, N minus 1 is equals to 2, which means the max value for L is 2. If there is a gap between 0 and the max value, we need to add 1 unit until we reach the max value. Let's start here from 0. Let's add an unit, 1. The next unit will yield the max value. Therefore, for N equals to 3, there are only 3 possible values for L that will satisfy the Schrodinger equation. And those values are 0, 1, and 2. Let's use the same idea to figure out what are the values that are possible when N equals to 4. Now we are going to move one shell up, going to N equals to 4. The first value possible for L is always 0. All the shells will have L equals to 0. And that will go all the way to N minus 1. For N equals to 4, we have 0. N minus 1 is equals to 3. Therefore, we have a gap between 0 and 3. So what we are going to do to fill the gap is start from 0 and add 1 unit until we reach the max value. 0 plus 1 is 1. 1 plus 1 is 2. And then 2 plus 1 is the 3, which is the max value. Therefore, for the shell number 4, there are 4 possible values of L. 0, 1, 2, and 3. Those values are the only ones that will satisfy the Schrodinger equation. And in a few slides, we are going to start calling L as orbitals. Okay, so that's going to be the future of the angular momentum quantum number. They're going to be baptized as orbitals. Okay, so let's move on here. So now I would like to build a table with uh, some possible values of n, or the number of the shells, and what are the allowed values of L. Change color here. For n equals to 1, the only possible value for L is 0, because n minus 1 is 0, and L has to start from 0 and go all the way to n minus 1. So n minus 1, the only value for L is 0. For n equals to 2, we can have 0. So let's do one thing. Everybody will have 0, because that's where things start. For n equals to 2, we can have 0 and 1, and that's the max. For n equals to 3, we start from 0, and our max is n minus 1, which is 2. Therefore, we have to fill the gap. For n equals to 4, we start from 0, and the max is 3. We need to fill the gap with units, 1, 2, and the next one is 3. For n equals to 5, we start from 0 and go all the way to n minus 1, which is 4. Now let's fill the gaps, 1, 2, and 3. Okay? And then n equals to 6, same idea here, starts from 0, goes all the way to n minus 1, which is 5 in this case. And then let's fill the gaps with units. 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. And that those are the allowed values for each n. And finally, n equals to 7, max value is 6. Also possible values are 1, 2, 3, 4, 5, and 6. Okay, so higher the number of n, more values of L are possible. And remember that n is basically the number of the shell. If you think about, the first shell is very close to the nucleus and can have only one value of L. What does that tell you about the number of electrons that can populate this shell? Think about that. As you move further, you can have more values of L possible. What does that tell you about the number of electrons that the seventh shell can handle? Think about that. You don't need to answer me. Let's move on with the plan here. Okay, so each value of L receives a label, and this label is going to be a letter. For L equals to 0, that's going to be called S orbital. For L equals to 1, That's going to receive the name of p orbital. L equals to 2 is the d orbital, and 3 is the f orbital. And after that, we follow the alphabetical order. Okay, F, G, H, I, and etc., etc., etc. Therefore, now if we add the orbital labels to each value of L as a function of the shell, we are going to get to something like that. For the first shell, we just have an s orbital. For the second shell, we can have an s and a p. The third, SPD, fourth, SPDF, and so on. Okay, all the way to the seventh shell, which can have S, P, D, F, G, H, and I. And that's very similar to something I showed you earlier in the course, how you distribute the electrons among shells and subshells. Okay, now we are going to use, instead of subshells, the word orbital. On the diagram that I showed you, we don't have 5G, or we don't have a 6F, and neither a 7I. Why? Because the elements that we know, we don't have enough electrons to fill those orbitals. Doesn't mean they do not exist. They are there. They, because there are not enough electrons, they are not populated, but they are there and they can be populated under special conditions. Okay, see here that the Schrodinger model follows a linear mathematical kind of thinking. So we start with probability. Let's try to find a wave function that describes the probability. And to solve these wave functions, we have to use the called quantum numbers. And each quantum number will have a correlation with the solutions of the wave function. And they are necessary to solve the wave function. First quantum number that we saw is the principal quantum number correlated with the number of the shell. The L quantum number is correlated with the shape of the orbital. We are going to talk a little more, and is a function of n. And as we can see here in the table, we have all the possible values for L as a function of the shell. Okay, so before we move on to the second part of the wave function, I would like to talk a little bit about radial probability. The radial probability is correlated to the probability of finding the electron as a function of the distance. Our reference is always going to be the nucleus. To find the probability that I'm going to represent by P, that's going to be equals to the radial wave function squared, okay? The square here is important to in order to eliminate negative values, times the derivative of the volume of a sphere. So we want to find the probability per unit of volume. Imagine an onion. The center of the onion is the nucleus, and the electron is moving anywhere inside the onion. Each shell of the onion is an element of volume, and we are going to find the probability per element of volume. And that's the reason we are going to multiply by the derivative of the volume. So that's going to be equals to the radial wave function squared. The derivative of the volume of a sphere is 4 pi r squared. Okay. And that will give us the probability, and we are going to graph as a function of the radius. To illustrate what I'm talking about, let's consider the orbitals 1s and 2s. Okay? First shell and second shell. What can you tell about the probability of finding the electrons as a function of the radius for the electrons in the 1s orbital and in the 2s orbital? Which one would be the closest to the nucleus? And which one the probability is higher, further from the nucleus? So think about that. While you think about that, I'm going to draw the axis here. I'm going to do a big one. Okay, so I'm going to stack both graphs here just to be more convenient. And here is going to be probability, which is equals to the radial wave function squared times 4 pi r squared as a function of the radius. Okay, so let's start. So let me do a thing here. I think it's going to be better. So let's draw them separated like that. And here is the same thing. Probability as a function of the radius. And then this is going to be for the 1s orbital, and here for the 2s orbital. Okay, which one is more likely to be found very close to the nucleus? It has to be the first shell, is the very first shell, is the best seat in the housing. It's the one closest to the nucleus. If we graph this function, we are going to get something like that. Oops, and it goes to 0. This point over here, this is the most probable position to find a 1s electron. It doesn't mean it's going to be there, but it's very likely to be there. There are two important points in this graph. The first one is right here. And for this point, the probability is equals to 0. And there is this point over here. So if we move far from the nucleus, the probability is also 0. Every time you graph probability as a function of the radius, you will have these 2 points where the probability is 0, or in better words, it tends to 0. It's so small that tends to 0. So always at the point 0, 0, which is our reference, and it's the nucleus, the probability tends to 0. And think about that. If you go so far away from the nucleus, the electron, there is no reason for the electron to be there. There is no attraction. Why the electron is going to be far from the nucleus? Therefore, when you move to the infinity, the probability also is going to tend to 0. Okay, now let's try to draw the probability for the 2s orbital compared with the 1s orbital. First thing, because it's the second shell, it's more likely to be found after the first shell. And if we graph the wave function for the 2s orbital, we are going to get a little hump here, and then higher probability as a second hump. And when it tends to the infinity, the probability is going to tend to 0. Therefore, this point over here, that's the most likely spot to find a 2s electron. However, there is also a small probability to find it very close to the nucleus. Okay? So again, here we have these 2 points where the probability is equals to 0. However, now for the 2s orbital, we have a third point right here where the probability is basically 0. When we have probability equals to 0 in between 0 and the infinity, this point is labeled as a radial node. And that's a point where it's very unlikely to find an electron. Okay? Radial node. Remember, the definition of radial node is when the probability is 0 and the point is in between the nucleus and the infinity. Okay? That's where a radial node must be. And there is actually a formula to calculate the number of radial nodes, and that's equals to n minus L minus 1. For the first shell, n equals to 1, we are talking about the s orbital, therefore L equals to 0. 1 minus 0 is 0, minus 1 is 0. Therefore, 1s orbitals do not have any radial nodes. However, when we move to a 2s orbital, now n equals to 2, L is still 0, minus 1 gives us 1 radial node. And it is right here in the graph. Okay, so this lecture is going to be a little bit extensive, but we need to cover some things here before we move on. Okay, And here I'm showing you some of the radial wave functions for some values of n and l. So if you know how to use some kind of graphing program, for example, Mathematica or MathCAD, you can square the functions, multiply by 4 pi r squared, and graph this as a function of r. And then you are going to get all the probability graphs. Okay, so I am showing here the radial function for 1s orbital, 2s, 2p, 3s, 3p, and 3d. Okay. Z here in the equation is the atomic number, and A0 is a constant called Bohr's radius. Okay, so you can find that in the book. Okay, so now let's talk about the second part of the equation, which I labeled as angular function. Okay? And the angular wave function YLML is a function of theta and phi. The wave functions that describe the YLML are dependent on two quantum numbers, L, that we already discussed, and ML, which is the magnetic quantum number. And again, there are only a set of possible numbers for L and ML that will solve the Schrodinger wave function, the Schrodinger equation. We already discussed L, so let's move on to ML. The magnetic quantum number is related to the orientation of the magnetic momentum of the electron in the space, and is a function of L. So because the electron is a charge and this charge is moving, that creates a magnetic quantum number. And the magnitude or the orientation of this vector related to the z-axis is the meaning of ML. ML must assume only integer numbers starting from minus L and going all the way to plus L. Okay, so ML will give us the orientation of the orbital in the space. That's our goal for ML. So let me show you one example here. How can we find all the possible MLs for a determined value of L? If L equals to 1, when L equals to 1, the label of this orbital is going to be a p orbital. Careful with that, okay? What are the possible values of ML for L equals to 1 for a p orbital? ML will start from minus L, therefore minus 1, and go all the way to plus L, plus 1. If there are gaps, we are going to fill the gaps with integer numbers and add 1 unit at time. Okay? So we have here minus 1, that's the minimum, plus 1 is the max. There is a gap there. Let's add 1 unit. Minus 1 plus 1, that's 0. 0 plus 1, that's plus 1, which is the maximum. Therefore, if L equals to 1, we can have ML minus 1, 0, n plus 1, which means that for the p orbital, we can have three different orientations in the space. And that's the meaning of ML, okay? Orientation of the orbital in the space. So let's do here a quick table about the possible values of ML depending on L. If we have an s orbital where L equals to 0, the only possible value for ML is 0. Okay? Minus L, 2 plus L, that's going to be the only possible. For the p orbital, we already saw that's minus 1, 0, and plus 1. D orbital starts from minus 2. That's the minimum value possible, and goes all the way to plus 2, minus L plus L, minus 2 plus 2. Let's fill the gap, adding 1 unit at a time. Minus 2 plus 1 is minus 1. Minus 1 plus 1 is 0. 0 plus 1 is plus 1. Plus 1 plus 1 is plus 2. Therefore, for the d orbital, we have 5 possible orientations of this orbital in the space. And last that we are going to do here is the f orbital, minus 3. That's the minimum. And that goes all the way to plus 3. Okay, minus L all the way to plus L. Minus 3, next one is minus 2, minus 1, 0, plus 1, plus 2, and plus 3. All right. For each orbital, we have different orientations that will yield different shapes. And those are the orbital shapes that we will find. For the s orbital, there is only one orientation possible. Okay, and here is the s orbital, which is a sphere. For the p orbital, three different orientations. So we have two lobes. The first one is called px, so the lobes are on the x-axis. Second one is py, the lobes are on the y-axis, and pz, the lobes are on the z-axis. And those are the three different orientations. We don't know which one corresponds to each ML, okay? So we know that there are three possible, but we cannot assign the MLs. The d orbital, we saw that we have 5 possible. dz squared, dx squared minus y squared, dzx, dyz, and dxy. Those are the 5 different d orbitals. And for the f orbital, we have 7 possible possibilities, and they are all drawn here. Okay. Each of those orbitals can house 2 electrons. Okay. For each individual orbital, we house 2 electrons. For example, px house max of 2, py max of 2, and pz max of 2. Therefore, the whole p orbital will house 6 electrons. Okay. Okay, and finally, the fourth number is used to differentiate two electrons, and the fourth quantum number is called MS, or magnetic spin quantum number, and is used to differentiate when there is more than one electron in the same orbital. There is a misconception of the magnetic spin quantum number. It does not have anything to do with rotation of the electron in its own axis. So that's a wrong concept. MS is basically a mathematical trick used to solve the Schrodinger equation. Okay? There are only two possible values for MS, plus half or minus half. And those are the only two values that will solve the equation. Okay, so think about one thing. The four quantum numbers are used to describe an unique electron. If we have the four quantum numbers, we can tell basically everything about this electron. So imagine that we have an atom, and that's going to compare as a whole country. Inside the atom, we have shells. That's going to compare to the states that are part of the country. Inside the shells, we are going to have subshells, and that's going to compare with city. Inside the subshells, we have orbitals, and that's going to be the streets of the city. And inside the orbitals, we have spin. And that's going to be the number of the house. To provide an accurate location of a person, we need to know number of the house, street, city, state, and country. And here, shell is given by the principal quantum number n, subshell by L, orbitals ML, and spin MS. Okay. Each electron has a unique set of the four quantum numbers. You can never ever have the same quantum numbers for two electrons. Okay? That's a violation of the Schrodinger equation. Okay, and then if we split the table in a very nice way to match the energy diagram levels, we are going to have something like that. Each square is a value for ML. And remember that each square can have max of 2 electrons. 1s, just one square, 2p, 3 squares, which are the 3 different orientations of the p orbital, d5, and f14. And that's how we are going to do electron distribution from now on. So let's start here with my first example. So I want to do the distribution for the argon, Z equals to 18. So let's start. Remember that we start from the lowest energy shell, which is the 1s. The s orbital has only one value for Ml, therefore can handle only 2 electrons. We are going to represent the 2 electrons in the s orbital by arrows. They are going to either point up or point down. It's a preference here. I like to start with arrow pointing up and arrow followed by an arrow pointing down. And here we have 2 electrons in the s orbital. Ms is equals to 0. After the filling of the 1s orbital, we move all the way up, and the next one to be filled is the 2s orbital, and that's going to accept 2 electrons, 1 and 2, and they have Ml equals to 0. Oops. After the 2s shell is filled, we move back up. The next one in energy is the 2p. Now the p orbital can accept 6 electrons because there are 3 slots. Each slot can handle 2 electrons. Attention here, because there are 3 slots, we have to follow a special order to fill these 3 slots. Imagine that you hop in the bus. All the seats are free. You can pick whatever seat you want. So let's suppose the first electron picks the first slot. The second person that hops in the bus, usually the second person is going to pick the next empty seat. And that's the same behavior with the electron. Now we are going to move to the second slot. The third person that hops in the bus is going to pick the last available empty seat. And we are going to fill the third slot. Now the fourth person does not have a choice. It has to sit with someone, and it's going to point down and go back to the first, then the fifth, and the sixth. Now the orbital is completely filled. We have to keep moving because we have 18 electrons to be filled along the shells. The next one is the 3s, and that's going to have 2. After the 3s, we move all the way up to the 3p, 6. 1, 2, 3, 4, 5, and 6. Oops, let's do this right way. 1, 2, 3, 4, 5, and 6. And with that, we completed 18 electrons, which is the number of electrons in the neutral argon atom. Okay, so that's why we start. The reason we start from the 1s orbital and go all the way up is because the 1s has the lowest energy. Okay, and then we move on throughout the energy diagram as needed. And here, keep in mind that full subshells are the most stable. Okay? Full subshells are the most stable. For argon, as you can see, all the subshells are completely filled, and that renders high stability to this element. And that's why argon can be found isolated in the nature. Doesn't need to combine with anyone because it's stable by itself because the subshells are full, completely filled. Okay, so let's do a second example here, and that's for the nitrogen. Nitrogen has atomic number equals to 7. If it's neutral, 7 electrons. Okay, so we have 7 electrons to distribute among the shells and subshells. Starting from the top, the first to be filled is the 1s, and it can house 2 electrons, one up, one down. The next one is the 2s, 2 electrons here, one up and one down. So far we distributed 4. To get to 7, we need 3 more. The next shell to be filled is the 2p, and it will house 3 electrons. 1, 2, and 3. Okay. So now look here, nitrogen does not have all the subshells completely filled up. Therefore, it is not stable by itself. However, it's not that bad because we have here the 2p subshell half filled, and that's very special. Half filled subshells are the second most stable. Okay, is not as stable as a full subshell, but it's not that bad. It has some sort of stability. However, it will tend to complete to fill up the shell. Okay, and each electron here will have an unique set of quantum numbers. Okay, so we talked a little bit about the off-bow principle, and that's the order that you follow to fill the shells and subshells, starting with the lowest energy and moving on. Okay, and that's the direction of the arrows. I showed you the Hund's rule. That means the electrons must be placed in the orbitals to give the maximum total spin possible. And that's what I showed you here. Okay, so you fill the first slot, second slot, and then third slot. And that's the Hund's rule. And then I will show you the Pauli exclusion principle, which means each electron must have an unique set of quantum numbers. So let's see how that works. So for convenience, so let me change colors here. So let's draw a blue electron up and a red electron pointing down. Let's determine all the quantum numbers, all the four quantum numbers for the blue electron and for the red electron, starting from the blue. For the blue electron, N is equals to 2, because it is located in the second shell. L is going to be 0, because the label S means L equals to 0. ML, the electron is located in the only ML possible, which is 0. And the fourth quantum number is MS. Here, the MS, we will have to follow conventions. So I like to assign MS plus 1.5 for electrons pointing up. Therefore, the MS for the blue electron is going to be plus 1.5. And let's do the same thing for the electron pointing down. Electron pointing down is also in the shell number 2, is also in the L equals to 0 because it is in the subshell S. The ML is also 0 because that's the only possibility. However, the MS is going to be the inverted sign as the blue one. Therefore, minus 1.5. And that's the Pauli exclusion principle. Each electron has a unique set of quantum numbers. And that's the reason we need to define the magnetic spin quantum number, because that's the one that will differentiate between two electrons when they are in the same orbital. Okay. Okay, some things for you to think about. Uh, Two questions here. Are the following quantum numbers possible? N equals to 2, L equals to 2, and ML equals to 0. Can we have this orbital, or is mathematically impossible? And the same thing for N equals to 3, L equals to 2, and ML equals to 0. And here we have a big table with a summary of the four quantum numbers, symbols, name, possible values, and um, the meaning of each one. And with that is more than enough. I'm sorry that this was a very long lecture, but we needed to cover this part of chapter number 7. For next lecture on Thursday, we are going to talk a little more about the periodic table. Okay, so I hope you have a good day, and I will see you in person on Thursday. Okay, bye bye.